Alright, so let's take up as much of the assignment as we can. This is the first question and the only question from the communication portion. I want to do it before we go over the thinking question. So it says, if we were to just analyze the normals of these three planes, how could we determine if they intersect in a point? So let's just go over this picture from our lesson. This is from one of our lessons. Notice this is the only example where they intersect in a point. Now, in this one, you have we have planes that are parallel, planes that are parallel. In this case, you have two parallel planes. In this case, parallel. This one, you have two parallel planes. So you can certainly look at those normals to see if any one is a scalar multiple of another. And if they are, then you know it's, well, one of these situations. And therefore, it's not this one. But doing that method, although is good, doesn't exclude these two possibilities here. So there's another method we can use that would exclude all these possibilities in one shot. So that's what we kind of want to look at right here. So let's look at these normals. So the first one, if I were to just write them, N1, right, that's 1, 2, 3. That's a great normal. 1, 2, 3. N2 is 2, negative 1, negative 1, and 1. And our third normal is 1, 3, 2. All right. So from this, I want to look at, since the question wants us to compare normals, let's look at the normals. Now, if you notice, specifically, let's look at these two. Now look at those normals. Try to imagine those normals. So if I were to say, take this, okay, put it up against the whiteboard. Let's do that example of like the triangle one. I can have one here, and one here. Notice that if I were to draw the normals for each of them, this one would be like this one like this, and this one like this. Or in the other direction. The direction doesn't matter. The point is, I could draw every single one of those normals on the whiteboard. I have no need for some sort of three-dimensional space or hologram to try and draw a normal coming out or into the whiteboard. So that means all three normals for both this case and this case are on the same plane. We can use that to our advantage. Here's what we're going to do. We are going to do the triple scalar product. You guys remember this? We did N1, oh, I need to switch back to my pen. N1 dot N2 cross N3. So let's look at what this means again. If I do N2 cross N3, well, take any two of these vectors. The order doesn't really matter. I could have crossed two different normals. But if you take any two of these vectors and cross them, you'll get a vector that's going into or out of the board. And then if you do a dot product with this vector and the one on the board, they're automatically 90 degrees. So that'll give you 0. So this is a great test. If we do this triple scalar product and we get that it's equal to 0, we know that it can't be these situations. The only situation, if you looked at all of these, the only situation where that triple scalar product would not give you 0 would be that first situation. So that's how we're going to tackle this problem. So N1 is 1, 2, 3. Dot the cross product. So cover these two. It's really easy to do the cross product if you write them one on top of the other. Sort of just cover your first ones, and then do negative 2 minus 3. So that's minus 5. Okay, and then cross the middle ones, right? And you get 1 minus 4. Okay, 1 minus 4 is negative 3. And lastly, sort of ignore the last ones, and you get 6 plus 1, right? 6 minus negative 1. So 6 plus 1, that's going to give us 7. Okay? And then we do the dot product. So that gives us 1 times 5 is negative 5. Negative 3 times 2, minus 6. And 7 times 3 plus 21, which equals 10, which does not equal 0. Therefore, they intersect in a point. Moving on then, the thinking question, and there's a reason why I'm doing one right after the other as I take them up. The thinking question gives us 3 planes and says find the value. This is actually a bit misleading. It just should say value of k, such that the 3 planes never intersect in a point. So we pretty much want anything but that one. If we want anything but that one, then we should do the triple scalar product and force it to equal 0. That way it's anything but that one. Now, the third plane has the k in it, so I don't want it messing up our little cross product there. So let's do n3 then. Dot n1 cross n2. And we're going to make that equal to 0. And then solve for k. Right, so n3 is 1, negative 1, negative k. Dot. And we want to do these cross products. So the n1 is 1, 1, 1, and n2 is 4, 1, negative 6. So the cross product would be negative 6 minus 1, 4 plus 6, and 1 minus 4. That'll equal 0. Alright, so 1 minus 1 and negative k dot negative 7, 10, and negative 3, forcing that to be 0. So that gives us negative 7, subtract 10, and plus 3k. Or 3k equals 17, or dividing by 3, k equals 17 over 3. So this question says find the equation of the plane that passes through the point and is perpendicular to the line of intersection of these planes. Okay, that makes it kind of sound like we want to first find that line of intersection for those planes. So we have plane 1 and plane 2. So let's look for that line of intersection. I'm just going to rewrite them over here. So we have x minus y minus 2z plus 3 equals 0. And we have 3x minus 2y plus z plus 5 equals 0. Now you can certainly set this up as a matrix if you want. I'm just going to go ahead and if this is plane 1, this is plane 2, I'm just going to multiply plane 1 by negative 2 and add plane 2. So it's the same steps you would do in a matrix. Okay, and that's sort of getting rid of our y's there, and it leaves me with just x plus 5z minus 1 equals 0. And I'm just going to let z equal t. And so x, just rearranging the equation, gives you minus 5t plus 1. And then I can go back to, say, pi 1. So from pi 1, I'm going to substitute those values for x and z and you get minus 5t plus 1 minus y minus 2z, which is t, plus 3 equals 0. Rearranging that for y, you get minus 7t plus 4. So those are our parametric equations for the line. If you like, you can write your vector equation for the line as just 1, 4, 0, right? Because that's 1, 4, and then 0 for z, plus t times negative 5, negative 7, and 1. Okay. So now looking at pi 3, our plane that we're looking for. Now the plane says, find the equation of a plane that passes through this point and is perpendicular to the line of intersection. Well, there's a line of intersection, and it has this direction vector. And if this direction vector is then perpendicular to the plane, it's a normal for the plane. So I can write the normal for this plane I'm looking for is minus 5, minus 7, and minus 1. Right? Now you can leave the negatives in there if you want, but just like a direction vector or a normal, really all that matters is the actual direction. Right? So not the magnitude. So I can pull out any scalar multiple I want. I don't like those negatives in the beginning, so I'm going to pull out a negative 1 and write it as 5, 7, and negative 1. But again, you don't have to. Right? So this is what I'm going to use then for the normal. 5, 7, and negative 1. And I can set up the equation then for the plane because those are your a, b, and c coefficients. So we have 5x plus 7y minus z. Don't know what d is yet, but that's going to all equal 0. So how to figure out what d is? Well, we haven't used this yet. This is a point on the plane. And if it's a point on the plane, its values for x, y, and z are true for that plane. So I can substitute them and figure out what d is then. So we'll have 5 times 3 plus 7 times 7 minus negative 1, and that'll equal, bring d to the other side, negative d. So there's 15 and 49 and 1. So d then equals negative 65. Or we can write our full equation as 5x plus 7y minus z minus 65 equals 0. Alright, so in this question we have in 3 space, find the distance between these skew lines. Now one's given in vector form and the other is given in parametric form. But remember, what we want to do is if we have skew lines, we want to find a normal for both, because that will be the shortest distance connecting those two lines. Essentially, we're finding parallel planes, right? Connecting those two lines at the shortest distance. So to find a normal for both, what we're going to have to do then is the cross product of their direction vectors. So our first direction vector looks to be 3, 2, 4. So 3, 2, 4. And our second direction vector over here in parametric form is 2, negative 1, and 3. Alright, so we'll do that cross product. Gives you 6 plus 4, 8, minus 9, and minus 3, minus 4. Gives us 10, negative 1, and negative 7. So there's our normal. And once we have the normal, we can figure out one plane. So those are your coefficients, A, B, C. Okay, so that was a good question. Yeah, you can use it in the different directions. in the different spots, and you would just get all these multiplied by -1. Doesn't matter which one you use. So we get 10x minus y minus 7z plus d equals 0. Alright, so that's a plane for, and it doesn't really matter if you choose to make a plane for that the second line lies on or that the first line lies on. I'm doing one for the first line, so what I'm going to do then is take a point on that line, which I know will therefore be on the plane, and I can solve for d. So that would be 10 times x, which is 1, minus y, which is 2, minus 7z, which is 3, equals negative d. So you can rearrange and solve that to get d equals 13. So what do we have now? We have a plane, which is which our first line lies on, and then we have another line, and we have a point on that other line. If you look at it, our point on this line, let's call it P, is 1, -1, and 0. So now we can use the equation we have to find the distance between a plane and a point. And that will be the distance, the closest distance between our skew lines. So just a reminder, our equation then is d equals ax naught plus b y naught plus c z naught plus d all over square root of a squared plus b squared plus c squared. And our a, b, c, d are just our coefficients in the equation of our plane 1, and our x naught, y naught, z naught is our coordinates in our point on line 2. That just gives us, so a is 10 times 1 plus b, which is -1, times y naught, which is also -1. Our last term, z naught, is 0, so it kind of disappears. And we have d, which we solved to be 13. And that's all divided by square root of a, which is 10 squared, plus -1 squared, plus -7 squared, which, throw those into your calculator, 24 over the root of 150, which you can simplify as 24 over 5 root 6. And that's approximately equal to 1.96. Alright, so for our true and false question, it says in 3 space there are 4 possibilities for the intersection of 2 lines. I honestly think this one could be worded better. I would go with true. There's not 4 possibilities for the intersection. I mean, you could have an infinite number of possibilities if the 2 lines actually line each other. But I think what it's trying to ask is 4 different cases for possible intersections or non-intersections, in which case you have where they intersect at a point, infinite intersections because they lie on top of each other, they're parallel, or they're skewed. So that's 4 different cases. So I would go with true with that one, but I do agree it should probably be worded better. Part B says skew lines are lines that are not parallel but line in parallel planes. Yes, that is definitely true. That's what skew lines are. Part C, a line will always intersect with a plane. No, definitely false. You can have a plane like this and a line like that. That will intersect. Alright, so this question says write the scalar equation of a plane, because there'll be an infinite possibility, perpendicular to the xy plane and passing through the point 4, 2, 1. So try to imagine, I'll try draw 3 dimensions. Okay. So this is your xy plane right here. X, Y, and Z. So if we were to have a plane perpendicular to that, and goes through the point, where is it, 4, 2, 1. Let me make it a little bit higher so that it's kind of more distinguishable. Goes through this point, then you would have something like this plane here. But it doesn't have to be limited to that plane. Like I said, if this paper is your XY plane and this is your plane perpendicular, it can rotate around as long as the rotational axis is on that given point. You have an infinite number of solutions there. But let's just look at this because I can't draw an infinite number of planes. So we're just going to stick with this visual here. All right, so now any vector you pick then along the xy plane that's a direction vector for the xy plane will be the normal vector for one of these possible solutions. So you can pick a vector that is, say, like this, and that vector would be 0, 1, 0. That's a vector on the xy plane, which would be perpendicular to one of these planes, that is perpendicular to the xy plane. You could also pick this vector, 1, 0, 0. Right? Now, this vector obviously isn't perpendicular to the one I've drawn, but it would be perpendicular, not to this one, but to that one, which is still a plane perpendicular to the xy plane. Similarly, you can pick change color. Take this one, something like this. That would work as well. 1, 1, 0. Right? So they only give you one point that's on the plane, so that means we can have an infinite number of planes that work. And therefore, all of these direction vectors are possible direction vectors you can use that would act as a normal vector for your plane. And so what you would do then is, I'm going to use 1, 1, 0. And so our plane then is x plus y plus d equals 0. Because I used 1, 1, 0 as my direction vector. This is, again, one possible answer. Not the only answer. There's an infinite number of answers. So now to solve for d, I use the point. And so it would be 4 plus 2 equals negative d, so d equals negative 6. And our plane then, for one possible plane, is x plus y minus 6 equals 0. Now you said, what about this vector? 0, 0, 1. Now that vector is going to be normal to the xy plane. So it's not on the xy plane, it's normal to the xy plane because it is this vector here. That's 0, 0, 1. But what you can do is you can look at this plane and you can pull out a normal for the plane that you found, which is 1, 1, 0. And the normal for this one, and their dot product should be 0. Because they're perpendicular planes. Because they're perpendicular planes, the normals to each of those planes should also be perpendicular, and therefore their dot product should be 0. So it's a check that you can make for yourself. In this case, you can probably see real quickly, 0 times 1 is 0, 0 times 1 is 0, and 1 times 0 is 0. So yeah, it equals 0. This one says determine the point of intersection of 3 planes. So what you'd want to do is set up your matrix. But notice the third plane is not in Cartesian or scalar form. It's in vector form. So we need to work with that first. So to figure out what the Cartesian form is, we need a normal vector. Now, since we have two directional vectors, we can find their cross product to figure out what the normal vector is. So the normal vector would be 2, 1, negative 1 cross for 0, negative 1. Okay, and that's going to give you, I'm going to do this quickly. Okay, you can check the cross product yourselves, but it would give you that. And to make things nice, I'm going to pull out a negative 1, because you can use any normal or scalar multiple of as your normal vector. And so we have x plus 2y plus 4z plus d equals 0. So we're going to need a point on that plane to figure out what d is, and that point is right there, 1, 0, 1. So when you plug those in for x, y, and z, you should get d equals to negative 5. So now you can set up your matrix. So you have 1, 3, negative 1. And that equals negative 9. Your next equation is 1, negative 1, 1. And that equals 11. Because I'm bringing our d term to the other side of the equation. And then with our new one, we have 1, 2, 4. And that equals 5, bringing it to the other side. And if you do some matrix mechanics here, right, it's actually called Gaussian elimination, but you should end up, and do this magically here, with 1, 3, negative 1, negative 9, and 0, 1, minus a half, minus 5, and 0, 0, 1, and 2. You can continue going, but what you should get is x equals 5, y equals negative 4,